ECC 3129 and 3119 electronic communication circuits. Hopefully you are in the right class. This is week 10. We are almost at the end of our semester. Another 4 weeks to go. I'm excited to finish this. I hope you are excited as well. Not because I don't like teaching you guys, but it's a tiring semester. So let's get it done with. And then you guys are in third year semester 2 and then final year. So time flies very fast. So today we are going to talk about pre-emphasis and de-emphasis network. Yesterday or last week, last week we talked about PLL, phase locked loop, and we discovered that phase locked loop is actually a feedback system, and that is the first time that we saw a feedback system for a communication receiver. And a feedback system is quite advanced because it is not easy to do. Typically, it's only straightforward. You have your amplifier and then your modulator and then you transmit it. There's rarely an occurrence that there is feedback involved. So feedback mechanism such as PLL and PLL frequency shift keying generator is quite advanced, at least for this class lah. Okay, let's draw. So pre-emphasis and de-emphasis network is a type of circuit that is typically employed in a system. For example, you have your transmitter communication part. You want to improve the signal to noise ratio before you even transmit it. So you will be using pre-emphasis. So pre-emphasis is it's almost like an amplifier, but it's different. It functions the same except slightly different. So we'll discuss what is the difference between a pre-emphasis and also an amplifier. And de-emphasis is actually suppressing your signal. It almost is like an attenuator, but it's slightly different. And again, we will discuss that as well. Okay, so pre-emphasis, we are always striving to develop new technology. We are always striving to develop new technology to reduce noise signal in transmission to improve audio signals and listening experience. So in FM, when we transmit a signal, the high frequencies are more affected by noise. For example, this is your signal. This is the frequency domain, by the way. Okay, and this is voltage or amplitude, power, doesn't really matter. And this is the frequencies inside your message. For pre-emphasis, it will emphasize or amplify the higher frequency components. Because why? Because these components are more affected by noise. Why? Because that's how just noise is. It likes to distort the high frequencies because noise is also high frequency itself. So when it gets transmitted, right? When it gets transmitted, so your signal will become, the noise, maybe it's going to spike like this. So we don't want this. So the way that we try to minimize this effect after transmission is that we employ our pre-emphasis in yellow. So how does it behave? We'll talk about it in the next slide. So emphasis and pre-emphasis. Pre-emphasis is used before FM signal. Okay. And it boosts a range of high frequency. So in yellow, it boosts a high range of frequency. De-emphasis is used after FM signal is received. It reduces the same range of frequencies that was boosted earlier. Okay, so let's try to imagine how it is boosted now. So this is after boosting. Okay, I'm trying my best to draw this in a similar shape. Okay, let's assume it's similar. Okay, after boosting, we start here, right? Okay, it will become slightly bigger. Okay, so this is the emphasized part. Emphasis, emphasized. So it emphasizes or it amplifies the higher frequency range before it is transmitted, and then after it is transmitted, your receiver will receive this guy and passes through de-emphasis. Okay, we are just discussing this conceptually. Of course, we have a block diagram and everything after that. So this guy gets passed through the de-emphasis, and de-emphasis will do the opposite of what emphasis just did. Let's use a different color. Let's use orange. So it will de-emphasize this part or this region, okay? And what we will get is a shape that is similar to what we wanted to transmit earlier, the original signal before it was emphasized or before it passes through pre-emphasis. Basically, it's amplifying the high range and then attenuating the high range. So what is the purpose of doing this? When you de-emphasize the high range after it has been distorted by noise, you are actually attenuating the noise as well, and that's a good thing because you are attenuating the noise. So what you will get, of course, you're not going to get the perfect original shape, but your noise is going to be smaller. So for example, oh sorry, I'm struggling with the colors here. So for example, this was the highest noise spike, right? After distortion, maybe it's just this much. Okay, so it's not that much. So you will get quite a good SNR. Again, the aim is always to preserve a good SNR. A high signal to noise ratio is good. Signal over noise. Signal needs to be bigger than noise. Okay. Okay, so that was roughly what was happening. So here we start with our message, and then we have our pre-emphasis filter. It is a high pass filter. Okay, and then we have our FM transmitter. It's typically an antenna, and then this is our medium of transmission. It's typically air, and then we have our antenna receiving our signal, and then it passes through de-emphasis. Now, what I explained here was a bit off because I was talking about frequency and then I put the spike like this. That's not correct. The spike would exist like that in the time domain only. So in the time domain, we know this, it behaves like this, right? And for FM, it is immune because we get to cut the top and bottom. We get to cut the noise in frequency. But sorry, in the time domain. But in the frequency domain, that the noise does not look like that actually. Silap, I was wrong. It typically exists between the frequencies. It's like random frequencies flying around in between the signal. Okay. In the time domain, yes, it is on top and below. And for FM signal, you can easily cut this off. We've discussed this before. In the frequency domain, the frequencies exist between the signals, so it's quite hard to get rid of it. So we just attenuate the high range frequencies. Okay. All right. So pre-emphasis and de-emphasis. So refers to boosting the relative amplitudes of the modulating voltage for higher audio frequencies from 2 to 15. So here we have our function, transfer function. We have our function. Here from 0 to 2, nothing happens. So 0 dB might means you're not amplifying, you're not attenuating. But once you hit 2 kilohertz frequency, the pre-emphasis will go up, which means that it's going to amplify this range and beyond, the range beyond 2 kilohertz. And then for the de-emphasis part, it will attenuate 2 kilohertz and beyond. So for this to work, the pre-emphasis must match the de-emphasis attenuation. So as much as it's amplifying, the de-emphasis should match with the same equal attenuation, okay, by the same amount. So this technique helps maintain a good SNR and allows the signal to travel a greater distance. So when our signal is distorted by noise, if you design your transmission to be, let's say 10 kilometers, it's quite short, but let's work with it. Let's say you design your system to transmit signal effectively within 10 kilometers or a maximum of 10 kilometers. But sometimes when there's rain, when there's fog, when you have deforestation, it's very smoky, so there's a lot of particles in the air, so it's going to affect your transmission. So instead of 10 kilometers, it becomes like maybe 8. So this is what happens when we have noise in the medium of transmission. So with pre-emphasis and de-emphasis, we get to conserve the SNR so that it remains 10 kilometer or it performs better. So this is the function. Okay. Okay. So this is the pre-emphasis and de-emphasis circuit. So this is pre-emphasis circuit. We start with our signal over here. Let's just call this MT. And this MT travels through a parallel, banyak pula construction. There's the construction going on around in my house. My son is screaming upstairs, but I don't think you can hear him. But I can, so it's a bit bothering me. So my modulating signal goes through this parallel circuit of capacitor and resistor, and then passes through a resistor over here. So pre-emphasis circuit is basically a HPF. HPF is high pass filter. High pass filter means that it's favoring the high range frequencies. So in the pre-emphasis circuit, R1, R2, and C form a high pass filter. The audio signal is applied to the input. This is our audio, assuming this is audio signal. The output is taken across the capacitor or across here. Below is a high pass filter with a truncate. Ignore this part. We are not dealing with transfer function in this class. And then for de-emphasis circuit, we are trying to flip what happened with pre-emphasis. We start with our FM signal that has been transmitted. It is demodulated first. Okay, demodulated first, maybe through a balanced demodulator. And then it passes through a de-emphasis circuit where it's going to attenuate the high range frequencies. And this is done through R, resistor, and capacitor. So RC form a low pass filter or LPF. HPF. Okay. So it's very simple circuit. Of course, this is the basic one. There is complex ones out there that really does the job well. So this is just the basic. Okay, so something to take note here is that your signal starts with pre-emphasis and then modulation. For this scenario, you start with your FM, you demodulate it first and then de-emphasis. Basically, you're reverse engineering. So this is, how do I say this? Preamp, modulate, demodulate, DM. So it's symmetrical, okay? If you can't remember, just imagine it's like a mirror. So you are just mirroring back what has happened in the transmitter side. Okay. Okay. Let's take a 10-minute break. Sorry, 7-minute break. Let's come back at 11:30. So if you have any questions, you can ask me, or otherwise, please take your break. Okay. Okay, let's continue. Oh, lagi seminit. Okay, let's continue. It's 11:30. Okay, so this is the pre-emphasis and de-emphasis filter shown here. This is a graph of frequency versus dB. So here we have a 1 kilohertz, 10 kilohertz, and 100 kilohertz. And over here, it starts to, take off a bit, not too much. And assuming this is 2 kilohertz, I'm assuming it doesn't give, oh, it does. It says here plus 3 dB at 2120. So it's saying that the filter starts to amplify at 2120 hertz or 2.12 kilohertz. And this is where it starts, and then it takes off up to plus 17 dB up to 15 kilohertz. So the typical values is 2 to 15. And again, because the pre-emphasis circuit is actually this guy, we can actually tune it, but this is the typical figures. And then we have our de-emphasis. Our de-emphasis starts from zero, no wait. So it starts at minus 3 dB at 21 here. So this is where it starts to, this is where they consider the attenuation to start at minus 3 dB. And this is where they consider the amplification to start, which is at plus 3 dB. Why plus 3 dB and why minus 3 dB? Because it amplifies or attenuates by half. Half is a lot, right? But that's just how optics are. Optical, they like the word 3 dB. Okay, so minus 3 dB, this is where it starts to attenuate. At least they consider the attenuation to happen significantly, minus 3 dB at 2120, and it tapers down to minus 17 dB at 15 kilohertz. Okay, so that's just how the filter looks like. This is a simplified representation to make us understand better. Of course, it's not perfect. You can see that this is this way and this guy is this way. Does it really cancel out the attenuation? Not perfectly, but it does the job. Okay, so comparison between pre-emphasis and de-emphasis. Pre-emphasis is a high-pass filter. It amplifies the high range frequencies. And then de-emphasis is a low-pass filter. It attenuates the high range frequencies. So let's compare what these two are. So high-pass filter, So this is frequency. High-pass will let the high range frequencies to be amplified, remember? And then low-pass filter attenuates, which means that it likes the frequency to be here. So this guy gets attenuated. This is not really happening much. This is amplified. This is attenuated because it doesn't let these guys, low pass filter favors low range frequencies, which means that the high range frequencies will be attenuated at some point. But they call this low pass filter because it kind of behaves like low pass filter, even though it's actually a de-emphasis. De-emphasis is much more technical than a low pass filter. A low pass filter is just basically a box, which we will learn in selectivity topic after this. Okay, so this is just to make you understand and relate to what we have learned actually. So it's not exactly like a low pass filter. It's more technical than that. Okay, but it's like a low pass filter. Okay, never mind that. Okay, definition, it boosts high frequencies. This guy removes high frequencies used at the FM transmitter, used at the FM receiver, and then implementation, high pass filter in transmitter circuitry, low pass filter in receiver circuitry. So the purpose is to compensate for expected attenuation during transmission. This guy restores the original frequency balance. And then advantage, improves SNR, and then applications, broadcasting, audio recording, digital communication. And then this is, de-emphasis is used is in FM demodulation, audio playback, communication receiver. Okay, this is what we have discussed so far. So any questions, you can read through this later. Any questions for me on pre-emphasis and de-emphasis? Is it okay? Everyone understands what's going on? I mean, it's just a different version of filters, right? So hopefully everyone understands. If they are still awake, wake up. Okay, let's move on to the next topic, stereo FM transmission, our radios. Let's move on. Okay, stereo FM, stereo broadcast transmission has transformed the way we experience audio content. You have your headphones, you have your AirPods. Now we have noise cancelling. Previously, when you guys weren't here on Earth yet, noise cancelling was not around. I was not brought up with noise cancelling. So noise cancelling is fairly new. And then when I was growing up, we had the stereo. When my parents were growing up, they probably did not have stereo yet. I don't know, I'm not sure. But before there was stereo, we had mono. What does mono mean? What does stereo mean? Does this class cover noise cancelling? I wish, but I can't find a textbook that talks about that. So I don't want to lead you astray. So I'm going to wait for a textbook to actually document that teaching, and maybe I'll have it in my next class. So basics of mono FM. In mono, only one audio channel is transmitted, which means that if your right ear is hearing the sound, the left ear is hearing the same sound. So there's no distinguishing factor. So you're listening to the same thing, no experience, no special experience going on. It's just the same thing hearing here. If you're deaf, one ear, you're gonna hear the same thing as everyone, you know? So, I mean, not to be deaf, but if you're deaf, you're not really missing out if we are still in the mono FM era. So adding stereo information, two channels of audio are transmitted, which means that you have the left and right. And if you wear your headphones, the left is playing something else and the right is playing something else, and it creates like real world experience, like how we are here. So if my friend is talking to me over there and I have another friend talking to me over there, I'm listening to two sources of audio. So that is stereo. But if I only have one ear, if my friend is talking over there versus if my friend is talking over there, I can't really pinpoint the location because they are combined into one ear. So that is what mono means and what it feels like. Okay, just close your ear. You get the idea of mono. Okay, so why is stereo important? Because, you know, we always want to improve our experience in life, right? So that's part of it. So to achieve this without interfering with mono receivers, we need to combine stereo and mono together in existing receivers so that if the audio is in mono format, it still can process it. If the audio is in stereo format, it still can process it. So that's why your laptops, your handphones can play both. If they don't have the stereo audio, they can still play it. If they have the stereo, they can still play it. So for handphones, I believe the speaker is, macam mana? I don't remember. But if you like put it in landscape, I believe you could have the stereo experience. I'm not sure if it applies to all phones out there. Maybe I can look deeper into that later. Okay, moving on. So this is the frequency spectrum of stereo FM. So here, let's talk about it first before everyone panics. So we start with frequency domain over here. This is frequency. And then this is power. Okay. So here I have one, what do you call this? Mountain. No, it doesn't look like a mountain. I have this one frequency component. I have this one frequency component. And it is situated between 0 to 50 kilohertz. Okay, looks like a blip like that. So this is L plus R, which means that this is mono. This region is specific to mono. Okay, so 0 to 15 is specific to mono. Okay, please bear this in mind first. And then we have our 19 kilohertz pilot. The pilot is kind of our carrier here. Okay, carrier. This is our information. And then using the same carrier, we double it to become 38 kilohertz. And then we modulate the information to become double sideband suppressed carrier. So here it's represented with a dash, which means that the carrier is suppressed here, and we are left with L minus R and L minus R over here. Why is it both L minus R? Because, how do I explain this? Because it is WC minus plus WR, and this is WC minus WR. So L minus R is actually this, omega R. Remember that we have our mixer. Okay, we have our mixer. This is our carrier, and this is our radio signal. Our radio signal is equal to L minus R. Now assume we don't know what L minus R is. Let's just say that it is omega R. So when you modulate or you mix these two signals together, what you're going to get is, remember these guys are cosines. So what you're going to get is a summation and minus of these two guys. WC plus WR, WC omega C plus omega R, omega C minus omega R. Remember, it's FC plus FM, FC minus FM. Same thing here. We're just changing it to omega. Okay, I hope everyone is still following me here. Don't sleep, wake up. Okay, omega C plus omega R. So now our omega R is L minus R, and omega C minus omega R is omega C minus L minus R. So basically what we're seeing here is just omega R. Okay, it's kind of confusing because we have the minus R here. No, it's not FM. It's not minus FM. L minus R is the FM. Okay. All right, so baseband is L plus R from 0 to 15. Pilot tone is 19 kilohertz. It's going to be doubled later to 38 kilohertz. And then you're going to get the SBSC signal. Okay. If anyone has any questions, please unmute yourself and ask away. Okay. Right. When listening to mono on stereo system, the normal procedure is to have the same sound playing in both channels. So what does the system look like? Let's take a look. Oh, ada lagi. Okay, for stereo, the trick is to convey the difference between L and R sounds by modulating a carrier at 38 kilohertz. In practice, this appears as a mirror image over here, components either side of 38 kilohertz. The diagram represents this blue shape, oh, they call it blue shape, representing the audio information for an example of a mono sound, and the red shape representing stereo. So this guy is stereo, this is mono, right? Where is the diagram? Okay. Okay, maybe later on that one. Okay, let's talk about the system. Okay, I want everyone to focus. This is the radio system for the transmission part. Okay, so we have our L audio signal and R audio signal. Okay, it is passed through an adder circuit. Okay, so here we have an adder circuit or a summer. Adder or summer is the same thing. It sums the signals or it subtracts. So adder circuits does that. It adds and subtracts. So in this case, it's adding because there's a plus sign here. So L is supplemented to this adder circuit, and then we have our R audio supplemented over here as well. So what you're going to get is L plus R passes through a pre-emphasizer. Okay, and then it goes through, after it is pre-emphasized, we denote this as an apostrophe. So L plus R is now a L plus R with apostrophe to indicate the difference. At this point, the higher frequencies is amplified, as we have discussed for pre-emphasized just now, pre-emphasis. Okay, and then this is transmitted over here to another adder circuit. Okay, hold on this one. Now let's move on to this adder. We have two adders here. So one adder L plus R and another one is L minus R. So L over here is L and this guy is R. Okay, so L minus R through the adder circuit. And again, it is still pre-emphasized. So to denote the difference, we note this with a apostrophe as well. So this pre-emphasized L minus R passes through a DSP-SC modulator. So what on earth is that? That is basically a mixer. A mixer is basically a modulator, a demodulator, a DSP-SC modulator. What it's not is a PLL, because a PLL is more complex than a mixer. Okay, so this L minus R apostrophe is supplemented to the modulator. And then over here, we have a pilot of 19 kilohertz. Okay, how do we get this 19 kilohertz? It's maybe a crystal oscillator or maybe a tuned circuit. Most likely a crystal oscillator because it is stable. And then it passes through a frequency doubler circuit. Okay, remember we talked about this guy. We had a doubler, we had a tripler, we had a quadrupler. That's the thing. Okay, so in this case, it is a frequency doubler. So this guy passes through a frequency doubler, becomes 38 kilohertz. Okay. So now we have L minus R with 38 kilohertz mixed together. What will happen? We'll discuss that. And then the output of that will be passed through an adder circuit over here. The pilot signal of 19 kilohertz will also be added to the adder circuit. So at this point, this forms a complex broadband signal that looks like this. This is our pilot, 19 kilohertz. This is our L plus R apostrophe. This is our L minus R apostrophe with cosine omega c t. What does this mean? It means that it is multiplied together and we have not expanded it yet. But this is modulated with a carrier of 38 kilohertz. So basically your omega c in this case is 38 kilohertz, not 19. Okay, omega c is here. Okay, any questions so far? Semua orang macam faham sangat ni. I am impressed. Everyone okay? Thumbs up, thumbs down? Okay or not? Macam terpaksa je thumbs up tu kan. Tak apalah, I appreciate the thumbs up. Okay, ada tak thumbs down? Ada tak orang nak tanya soalan? No? Okay. Okay, so we discussed the other thing. So now let's discuss the mixer so that everyone that has forgotten about the mixer will remember. So this is like memory lane. So the reason for using a pilot 19 kilohertz rather than a 38 kilohertz is that it is easier to separate the pilot. Now, if we want to separate it later in the receiver, having the frequency over here is quite hard because it's sandwiched between two signals, right? And the pilot is like, hey, I'm alone here, so it's easy to construct a bandpass filter here, extract it out later. So that's why we stick with the pilot of 19 kilohertz rather than using 30 kilohertz and adding it here. Okay, so that's the reason. The stereo transmitter design must be compatible with monophonic transmitter. We discussed that because we need the L plus R over here. That's the mono part. Okay. Okay, so this is mono compatibility. Mono FM receivers only decode the L plus R component, ensuring compatibility with the older systems. So our system is a combination of mono and stereo right now. So stereo decoding, stereo FM receivers use the 19 kilohertz pilot tone to regenerate the 38 kilohertz subcarrier. The L minus R is demodulated from the subcarrier. The stereo channels are recovered as this. Nanti kita tengok, we will see how the system looks like, but this is the calculation. So L plus R plus with L minus R, and then you divide this by 2. Oh, let's go through the system first. I think the calculation would not make sense without seeing the system. Okay, so this is what we are receiving, the FM stereo receiver. So this is divided into 3 regions, and we will have 3 different filters to cater the 3 different regions. Okay, so the top part is the mono receiver part. The top part is the mono receiver part, the rest it belongs to the stereo. So LPF, low pass filter, extracts the L plus R emphasized here. NBF, narrow band pass filter, extracts the 19 kilohertz over here in yellow. And the band pass filter from 23 to 53 kilohertz extracts the L minus R cosine omega CT. Okay, and then it is passed through a synchronous demodulator, which is again a mixer as well. And then our narrow band pass filter is 19 kilohertz, extract the pilot signal, goes through a frequency doubler again. Therefore, this is 30 kilohertz once again. Okay, or omega C. And then these two guys are mixed together. What is left is going to be L minus R apostrophe de-emphasized. We are removing the apostrophe and we are left with L minus R. And then the L minus R is added to L plus R, and a bunch of calculations happen and you will get L and R separately. Okay, so how does L and R get separated? So this is where the equation comes into play. So L plus R plus L minus R, so you will have 2L plus R minus R gets cancelled out, divide by 2, you get L. Then L plus R minus L minus R, you will get 2R divided by 2, you're left with R. So that is what is happening at the adder circuit over here. Okay, nothing fancy, it's just a bunch of addition. Okay, so now let's talk about the mixer part, because we are at the end of FM stereo. We're not done with class yet. I'm going to give everyone a break after the mixing part. Okay, new slide. Draw this. Okay. Okay, so our modulator side, let's take this part. Remember, we have L minus R apostrophe with frequency doubled pilot, which is 38. So per 38 is omega C. This is L minus R. Okay, let's keep that in mind. So mixer part, modulate, transmitter, sorry. Transmitter. Okay, I am going to try my best to write this nicely. Okay, so we have our L minus R apostrophe, and we have our DSP-SC modulator, or basically a mixer. And then we are supplying with our 38 kilohertz or cosine omega CT. This in the actual form would look like cosine omega L minus R. Wait, let's just call this omega S. Let's call that omega S, okay? Omega ST. So what will happen here? So using your trig identity, okay, I'm just using the script from before. So you know how the trig identity is. So 1 over 2, you will, cosine X cosine Y equals 1 over 2 cosine X minus Y, or X plus Y first. And then plus cosine X minus Y, blah, blah, blah. You know this. Okay, this is just a recap. So let's use this trig identity. Cosine omega ST times with cosine omega CT, right? And then we will get 1 over 2. Okay, cosine omega S. Which one is the carrier? Which one is bigger? This guy is bigger, omega C minus omega S plus cosine, ya Allah, cosine, omega C plus omega S. Okay, so this is what we have. So let's look at the spectrum. The spectrum was like this, right? Two shapes. Okay, it's not like that. That's bad. Like that. Okay. So what on earth are these? So this is omega C, right? And this is going to be omega C plus omega S. And this is going to be omega C minus omega S. What is omega C plus omega S? Omega C plus omega S is basically L minus R apostrophe cosine omega C T. Same thing. This is not expanded. This is expanded. Same thing. It's just the same thing. And then this would be L minus R apostrophe cosine omega C T as well, divided by 2. So this is L minus R as well. So why is it DSBSC? Because if you notice here, we don't have our omega C existing alone. It's no longer there. Oh, sila. It's no longer there. So that's why it's represented with a dash, which means our carrier is suppressed. Okay? So this is how our radio, this is how we get our L minus R part. Okay? So that is the transmitter part. Let's go on to the receiver part. If you have any questions, you don't understand, please let me know. As usual. Okay. Oops. We need to keep our trick identity. I don't want to reuse the script. It's quite boring for me. Okay. All right. Okay, receiver part. Okay, bear with me. After this, we'll have our break. I know everyone is dying because we are almost mid-holiday. Don't die yet. Okay, receiver part, we have our synchronous demodulator, which I, pangkah over here. I put an X, that's the mixer. So what do we have here? We have L minus R apostrophe cosine omega C T, and we have our omega C supplied. So again, same case, same scenario. We're going to get the same thing back again. Okay, this guy is now L minus R. Yeah, I don't have space. Okay, for some of you, this part is pretty boring because maybe you are too smart for this already. But some of you guys need this explanation, so I need to do it, okay, to be fair to everyone. Okay. All right, so L minus R apostrophe cosine omega CT. This is what we are receiving. Remember, this is actually this dude over here. Okay, this is what we're receiving. And then we are supplying this omega C over here. So this is cosine omega CT. And again, what will happen at this point, we are going to add and we are going to subtract as usual at the mixer. So I think you already know where this goes. So this is going to be added together and this is going to be subtracted. So I'm going to write down the answer. So this is going to be 1/2 cosine, sekejap, susah lah pula. 1/2 cosine omega R, omega S, sorry. I wrote this R in my book. Sekejap. Okay lah. I'll do this properly. Omega C minus omega R minus omega C plus cosine, this is T, omega C minus omega R plus omega C T. Okay, now let's do the math. Okay, cosine 2 omega C. Oh my God, what happened to my omega? Looks like a bat. Okay, omega C, 2 omega C minus omega R T plus cosine. This guy gets cancelled out, alhamdulillah. No, sorry. This guy gets cancelled out. Wrong equation. minus omega r. This is omega c minus omega c. Omega r. This guy is 2 omega c minus omega r. I think I did this incorrectly. Okay, so this is what we have. Let me double check. Minus omega r. Cosine. 2 omega c. Sekejap. Okay. Omega r, sorry. I used omega r again. This is S according to our notes. This is omega S. Okay. Okay. So now you can see that this is cosine minus omega S. So cosine minus frequency jadi apa? I believe it's the same thing. So it will eventually become cosine omega S juga. And this is going to be cosine 2 omega C minus omega S T. So what happens to this dude? Why is it not, where does it go, kan? Because eventually we will get omega S, which is L minus R back again. So it means that this guy is eliminated, but how? Okay, so now remember that 2 omega C is actually 38 kilohertz times 2. This is 76 kilohertz. This is way too big for the system itself to handle. So typically it will be attenuated or filtered out. So any too high frequencies, gone. So it's just going to retain anything that is within range only. So let's go back to the system. For this part, the omega C times 2 is going to be too big for the system, and it's not going to be part of the transmission, part of the demodulation anymore. Or maybe they have some bandpass filter to get that out. But anything that is too high or anything that is too low for a system typically gets filtered out anyways through a bandpass filter. So in this case, they got rid of omega C, double omega C minus omega S. Okay. And what you're left with is L minus R omega. So let's say there's a question. They ask you what happens after the synchronous demodulator. What is the signal that you obtain? You would write down the calculations for that. I know this is very ugly, but you can rewrite this in your own beautiful way. You write the equation, what happens after the synchronous demodulation, and then if they ask what happens to the too high frequency, you say that it is eliminated because the system it's not appropriate for too high frequencies. That is the nature of all systems in radio frequency actually. When they have a specific range of frequency, if it's too high or if it's too low, they would just not process it. And it is a standard answer, by the way. Okay. Right, so that is FM stereo for you. So let's take a longer break than usual, 10 minutes. Let's come back at 12:13 p.m. If you have any questions on FM stereo, please let me know. Any questions on pre-emphasis, I welcome that as well. So let's take our break and come back later. Okay. This is super heterodyne. Okay. Okay, I just want to share with you guys that RF frequency is also used in cosmetics these days. So here we have, kejap, korang dengar tak dia punya suara?
Microneedling the traditional format.
You guys hear the
Downtime.
voice?
So RF microneedling might have a slightly longer downneedling targets. While both effectiveness differences, microneedling and RF microneedling.
For those who don't know, I think the guys don't know what microneedling is. Microneedling is basically a cosmetic procedure where they inject like many small needles into your skin to stimulate collagen. So now the advanced in cosmetic procedures, they are incorporating microneedling with radio frequency, which is our topic. So the radio frequency that they use is 1 megahertz to 2 megahertz. I'm going to show you how they do it, like simulation, of course.
Deeper layers, making it more
It's like
microneedling targets
see the
deeper
needles
layers,
as they
making
are
it more effective for skin tightening and treating severe acne
painful.
scarring. Now, the heat element. So RF microneedling uses heat energy, which further enhances the collagen stimulating effect. And this can help with creating a tighter skin, unlike microneedling the traditional format. Downtime. So RF microneedling might have a slightly longer downtime due to the
Okay, so microneedling is already very painful. I don't know how it feels like. I have never done it, but they combine microneedling with RF technology. So I tried to Google what the RF power is, and you would not believe this. It's very scary. So okay, I don't know where it is, but I read that it is 1 megahertz to 2 megahertz, and the watt frequency power is apa? 80 watt, up to 80 watt. Up to 80 watt. You can actually burn your skin like that. Of course, you always need to do this with a doctor. And microneedling with RF, of course, I had to read more on this. Microneedling with RF, they have not studied the side effects widely yet. So if anyone wants to do it, don't do it yet. Wait for the full report before you do any procedure. Not just microneedling, anything in life. Laser, facial, whatever it is, make sure you do your research well. This is for cosmetic. And any, stuff related to the boys, I don't know. But this is more related to the girls, I believe. But some of you have acne scars that are deep, right? Sometimes you want to go for microneedling. You can do that. Microneedling is well established. Microneedling with RF is not, so don't do it. Okay. I read more on this. There are a lot of patients that have burn scars because of the microneedling with RF. So it's very, very scary. Okay, tu je. Just off tangent. Okay, let's back to the presentation. So it's interesting that they use RF for that. I don't know why they use RF though. They don't have to, but they did. RF is like broader. Laser is smaller. Okay, never mind. Entire screen over here. Okay. Okay, so our next topic is going to be a bit complicated, like PLL a bit. So it is called the super heterodyne receiver. So it is, so our task or our aim is to identify, am I still recording? Yes. So our task is to identify the function of each component of a super heterodyne receiver, express the relationship between intermediate frequency, IF, local oscillator, LO, and signal frequencies mathematically and calculate any one of them given the other two. So explain how the design of dual conversion receivers, okay, maybe this will be next week. Okay, super heterodyne receiver. First of all, we need to ask ourselves, what makes a good communication receiver? The first parameter that we need to look for is selectivity, and the second one is sensitivity. So selectivity means that you need to means that the receiver is able to identify and select a desired signal from thousands of other present in the frequency spectrum. So let's say your signal is this, your audio that is being transmitted. But after it is transmitted through the medium of transmission, the noise makes it makes the signal that is transmitted to become an overlap of these two signals. So now you have a combination of the signal as well as the noise. So selectivity, a good selective receiver is able to identify what signal needs to be extracted out and takes only the signal, the desired signal. So that is selectivity, selecting. Okay, selectivity, selecting. So a good selectivity prevents interference, ensuring clear reception of desired signal. Even though we take out this chunk and there's noise, so maybe your SNR will go down a bit, but the signal is still there and we are not losing any signal. Okay, and then another parameter that we need to look out for is called sensitivity. It is the ability to detect and process the weakest signal to recover the modulating signal. Okay, and again, back to this scenario, if we are transmitting a signal, our signal looks like that, and our noise looks like this, what is the minimum that we need for our receiver to actually process the signal and not declare it as noise? If it is too small for the receiver and they see this part, oh, that looks like a noise, I'm not going to process it. I'm just going to, not just ignore this. This is noise. But for a good sensitivity receiver, it identifies this, oh, this is within the region that we are supposed to look out for. It has some SNR here, even though the SNR is really, really bad, but it is still signal. So we are going to try to amplify this, extract this, and make it work. So that is a good sensitivity. That is a good receiver. So that is a receiver with good sensitivity. Okay. Now let's talk about the details. So selectivity is again the optimum bandwidth that is not only wide enough to pass the signal and its sidebands, but also narrow enough to eliminate or greatly attenuate signals on adjacent frequencies. So if we are talking about narrowband FM, our narrowband FM looks like this. Maybe there will be some other noise frequencies. So our filter needs to identify this part. But of course, our filter is not going to be perfect like that. It's going to look like a blob like this, slightly pinched blob. So how do we control our blob, right? So our blob is dictated by bandwidth equals to resonant frequency over Q. The selectivity is obtained using LC circuit. LC dictates our FR, okay? And our R, our resistors, and our biasing voltage, our anything regarding the losses in the circuit will dictate Q. And these two values dictate the bandwidth of your filter. So BW is bandwidth. Okay. So FR is resonant. Q factor is changed by changing R and energy losses in the circuit. A well-designed receiver circuit allows Q to be tuned independently of resonance circuit. Now remember, our circuit is sometimes looks like this, and there's a bunch of combination of resistors. So how do we tune our Q without affecting our FR? So FR is dictated by this, right? Our inductor and LC and C. So this is supposed to be inductor. Okay lah, boleh lah tu. Our inductor and C. So how do we tune this without affecting our FR? Our FR needs to stay there, but the Q needs to be tuned so that we can control the bandwidth. Sometimes when you tune the Q, the FR gets shifted. That's a design that is weak, but it happens a lot, so it is pretty common. Okay. Is this the same thing? Yes. Oh, okay. I want to explain about this diagram. So here we have our blob here, slightly pinched over here at the top, and the top will be indicated by, should be here, 0. Why is it there? Good job. I'm not sure. Let me double check on this. Typically, we start from the top. That is our 0. And then going down, 3 dB minus 3 dB attenuation. This is where our F2 and F1 are. Sorry, F1 and F2 are. And F2 minus F1 will give us our bandwidth. Okay. So how does ideal selectivity look like? Ideal selectivity would have perfectly vertical sides like this, like a box. Of course, that's not possible. Such curve is not possible with tuned circuits. In the digital world, maybe, but for analogs, it's not possible. We can improve selectivity by cascading tuned circuits or using crystal oscillators as F or FR to maintain the FR and change the Q. That would be easy. Important to note that the receiver selectivity should accommodate the characteristic of information signal. Your FR should be tuned to where your desired signal is. For example, excuse me. For example, you are extracting L minus R from the FM. Where should your FR be? Your FR should be at omega S because L minus R is omega S. Okay, so that is what it means. You need to tune your filter to your desired signal. Maybe you're working with FC plus FM, one sideband, single sideband. Therefore, your filter needs to be tuned at FC plus FM, your single sideband resonant frequency. Okay, so this is the ideal response, and this is in the practical response, practical real-world scenario response. And then we have a new term called the shape factor. What on earth is a shape factor? A shape factor is a skirt. Doesn't really explain much, but this is our skirt. Yang kembang ni, the expanding part. Okay, skirt. Skirt, yeah, it does look like that. So this is our skirt. If you have a boxy figure, this is how your skirt looks like. If a guy were to use a skirt, wear skirts, this is how they would look like because they are boxy. So the steepness of the skirts or skirt selectivity is expressed as the shape factor. Okay, shape factor. We use this word shape factor a lot. What is it? Shape factor is bandwidth at 60 dB attenuation. Okay, what is 60 dB? This over here. Let me use a different color for that. 60 dB attenuation from the top, going down by 60 dB. This is the bandwidth for 60 dB. And this is going to be your top part. Forgot what the actual name is. So 60 dB bandwidth, and then divided by our 6 dB bandwidth. From the top going down by 6 dB, that is your bandwidth. How do you find out the bandwidth? You just minus the frequency. So F4 minus F3 gives you 60 dB. This guy. And then F2 minus F1 gives you 6 dB. So the delta F for 60 dB and delta F for the 6 dB, divide that together, you will get the shape factor. Okay, you know everyone's dying inside a little bit more. Okay, we have a few more slides. No, we have a lot more. Okay, tak apa. Let's just be strong together. Okay, let's assume that the 60 dB bandwidth is 8 kilohertz. Okay, this guy is 8 kilohertz. Okay, and then the 6 dB bandwidth is 3 kilohertz. Okay, so the shape factor will be 8/3. Always the bigger over the smaller. Always the bigger over the smaller. Always the 60 dB over 6 dB. Okay, so 8/3 will give you 2.67 shape factor. Or sometimes it is expressed as a ratio. Now, is a higher shape factor better or is a lower shape factor better? That's the question. So let's discuss. Let's do this example first before everyone dies on me. Okay, Maybe I'm going to give it 10 more minutes, okay? Okay, so bear with me, 10 more minutes, promise. Okay, a choice is to be made between two 10.7 megahertz IF filters. So abaikan this filter because we have not learned about it yet. So 10.7 megahertz filters, this is where the FR is. One has a shape factor of 2.3 and the other 1.8, which has a better selectivity. I know we have the answer here, but let's discuss it. So here our shape factor is given by bandwidth of 60 dB over bandwidth 6 dB. Okay, so let's observe this skirt. So a bigger skirt means that it is less selective. Why? Because let's assume this is our signal and this is what I'm trying to capture. This is FC plus FM, FC minus FM, our typical AM signal. And my filter looks like this. Okay, this is my first filter. And then I have a second filter. Let's do this in green. Looks like this. Okay, which one is better? Okay, if you agree that blue is better, thumbs up. If you agree that green is better, thumbs down. Okay, please vote. Which one is it? Green, thumbs down. Blue, thumbs up. Come on, guys. Kalau salah pun tak apa. It's not a test. Okay, a lot of you are saying thumbs up. Niao Lao Yiki is saying thumbs down. Sri thumbs down. Okay. So mixed opinions on this. Okay. What happens if you have noise? Now let's change this scenario and include noise. So let's call our noise the purple guy. So noise obviously happens in random frequencies. So, okay, assume ada sikit lah kat sini kan. Make it realistic. So for the blue filter, which is thumbs up, you are going to get the noise as well. But for the green filter, you are actually minimizing the amount of noise that you incorporate into your signal. So the answer is green. The steeper your skirt is, the A line, if A line is better than, what's the other side? What's another type of skirt? A line versus kembang, payung. No, wait. A line is this. Kan? And then there's another one like that. Okay. Assuming we are talking about the same thing. So the steeper your skirt is, the better. Okay. What makes a steep circuit? Is it a high shape factor or a small shape factor? Okay. So if our 60 dB is large, we have our umbrella skirt here, right? Let's call it umbrella, and then this is A line. Because why? It looks like an A. Memang it's called like that. I'm not making things up. It's called A line skirt. Okay. Umbrella, yes, that is made up. So A line skirt is steeper, which means that the 60 dB bandwidth is smaller. If this guy is smaller, which means our shape factor is smaller. Okay, shape factor is smaller. If your 60 dB is bigger, I should do this in different colors. Okay. So if my 60 dB is small, okay, 60 dB small will represent the green filter guy. It means that my shape factor will be small. Okay, bear with me first. And then if my 60 dB is high, it means that I'm going to get this kind of shape, right? The umbrella skirt. So my shape factor will increase. Therefore, our shape factor that is big or higher will make us have a poor selectivity. So this is poor selectivity, this is good selectivity. So smaller shape factor is preferable. Okay, I hope that was okay. Okay, we have another 5 minutes, bear with me. Okay, so that was shape factor and the skirt, A-line and umbrella. A tuned circuit has a resonant frequency of 18 megahertz. So this is our FR, 18 megahertz. and a bandwidth of 120 kilohertz. Okay, 120 kilohertz. What are the upper and lower cutoff frequencies? So again, let's read the question. A tuned circuit has a resonant frequency and bandwidth. What are the upper and lower cutoff frequencies? We're talking about a tuned circuit that is behaving like a filter. Doesn't explicitly say it, but it has the upper and lower cutoff frequencies. So assuming it has that cutoff frequencies, obviously it is a filter. So let's draw it. Our FR is this 18 megahertz, and then it's giving us delta F, which is 120 kilohertz. Now, assuming this filter is symmetrical, like that, like our blob that we've seen earlier, therefore, this will be a total of 120 kilohertz. It's asking upper and lower cutoff frequencies, which means that you need to provide values. So this is going to be 18 megahertz plus with 120 kilohertz divided by 2 for the upper, and this guy 18 megahertz minus 120 kilohertz divided by 2. This is going to be your lower cutoff frequency. Okay, what does cut off mean? Means cutting it off. Cut off. Okay, cut off. You're cutting it there. Okay, that's where you are cutting off the frequency. This is what you are allowing to be transmitted. That's why it's called cut off over here. Okay. Oh, we still have 5 more minutes. Okay, I'm just joking. 3 more minutes. Okay, now we talked about the selectivity. We did not talk about sensitivity yet, but I feel like sensitivity is too wordy to be discussed at this very critical hour. Let's talk about the system instead, and let's go back to sensitivity tomorrow. Okay, so this is a simple receiver versus not so simple receiver. So let's differentiate it, and then we'll talk more about it tomorrow. Okay, so this is the simple receiver. We start with our antenna. It is receiving anyway, that's why we start with antenna. We have a selector, which is our filter, and then we have our amplifier, which is this dude over here that we learned way back in week 2 and week 1. And then we have our demodulator, which is our mixer, and then we have another amplifier, and then we have our speaker, which will give us our FM, our original signal that we have gone through so much to receive, right? We have learned so much. Now we are at the receiver side. And then here we have our filter, we have our amplifier, another amplifier, mixer. Okay, this is simple, considered simple. Our not so simple receiver is this guy. We have a pre-selector, which means that it is going to pre-select from a mountain of frequencies. It's going to select the desired frequency, and then it is going to mix it, this desired frequency, mix it with a local oscillator. The local oscillator is typically a tuned circuit or sometimes a crystal oscillator. We have discussed this for VCO previously. We mix it together, and then we have an IF stage. This is called an IF stage. The IF stage has an amplifier and selector, which is almost similar to this guy. Now only we start over here, right? So we have our amplifier and our selector. Again, another selector. And then we have our detector, another mixer here. And then we have an amplifier here. And then we get our FM. Okay. This not so simple receiver is called the super heterodyne. The super heterodyne incorporates a local oscillator to really make sure that we get a good message back. Okay, let's talk a bit on the concept here. So why is the radio frequency changed? Sorry, that is skipping. So at the RF stage, we have our pre-selector, and then we have our mixer that is going to mix whatever that is filtered with the local oscillator, right? So at this point, it is down converted, okay, down converted into lower frequency. Okay, we will discuss how this is. Ya Allah, to my handwriting. It is down converted into a lower frequency at this point. You start with an RF frequency, normal one. You mix it, you are left with a lower frequency. This is the beauty of superheterodyne. Why? Why do we down convert it to lower frequency? Because it is easily processed and filtered. Okay, does that really make sense now? Later on, we'll discuss it. Okay, so I'm going to stop here before we get too technical. So I'm going to discuss sensitivity and the key block diagrams of superheterodyne receiver tomorrow. If you have not signed in your attendance, please do so using Putra Blast. The link is there. Do that. I'm going to record this and upload it. If you feel like you need to revise, please do. Otherwise, have a great rest of the day. I'll see you tomorrow online as well. Take care, everyone. Tomorrow? Yeah, tomorrow. Bye.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Right there.